Hello everyone, welcome to the recorded session on disinfection. This, let me just start with objectives. The class objectives for the week are, by the end of this week, and after all the activities that you do, you should be able to name the 4 major methods of drinking water disinfection and list at least one advantage and disadvantage of each. Describe 3 factors that increase or decrease the effectiveness of chlorine disinfection. Explain basic properties of chlorine disinfection, including why breakpoint chlorination is important. Describe uses, technology, operation, and maintenance for UV disinfection. Describe uses, technology, operation, and maintenance of ozone disinfection. And then, as a group, you're going to select the most appropriate treatment method for a given source water. Okay, so kind of cut and dry. Those are the objectives for the week. So the primary goal of water treatment is to ensure that the water is safe to drink and does not contain any disease-causing microorganisms. The best way to ensure pathogen-free drinking water is to make sure that the pathogens never enter the water in the first place. However, this may be a difficult matter in a surface water supply which is fed by a large watershed, which you've already explored a little bit with Charlie. Most treatment plants choose to remove or kill pathogens in water rather than to ensure that the entire watershed is free of pathogens. Okay. The other purpose is, of course, in ensuring that the water is safe to drink by complying with the safe drinking water laws. Now, what I'm trying to get across with this slide here is that it's not just during the disinfection process where the pathogens are removed from the water. In coagulation, the first 3 steps remove 90 to 95% of pathogens. In sedimentation, there is 20 to 70% removal by settling with the floc. And then during filtration, 20 to 99+%, depending on the filter media, is removed. And then at the disinfection point where the actual chemicals or physical processes are added to kill or inactivate the pathogens, that would be the last part of the water treatment process. So here's a list of pathogens that are frequently present in our water. We have bacteria, viruses, and parasites. And you'll see the list, the pathogen and the disease caused by these pathogens. So the goal of disinfection is to remove or inactivate all disease-causing organisms in the water. But testing for each type of pathogen would be costly and inefficient. And so instead, operators focus on 3 indicators of pathogen removal efficiency. Giardia to 99.9% removal, viruses to the 99.99% removal, and for coliform bacteria, the criteria is absence. If you take less than 40 samples per month for your particular system, then no more than 1 positive is allowed. If you take more than 40 samples, no more than 5% positive samples are allowed. And as you recall, we've started, I think it was in the Reg and Admin section, we looked at the site sampling plan for the city of Santa Rosa. When we do the water sampling lesson, we will talk a lot more about these testing requirements, how to do it, how to do retakes. So if you want to look back at that site sampling plan from Santa Rosa, please feel free to do that. But we will talk about that more frequently. But I just want to let you know by this slide that the criteria is absence of coliform bacteria. So, types of disinfection. So disinfection can be either physical or chemical. Examples of physical would be coagulation, sedimentation, filtration, or storage, as we already talked about. That disinfection happens through all of these processes. UV is a physical type of disinfection. You can heat it, apply heat, or ultrasound as well. And the UV and ozone have a little asterisk because we are going to cover them more completely throughout the rest of this presentation. The others I'm just mentioning for completeness. Oh, and of course chlorine. So the chemical parts. Chlorine is the most commonly used. Iodine, bromine, or ozone are other chemical forms of disinfection. And just to let you know, the next week's lesson is chlorination, where we are going to go way more deeply into chlorination. Tonight I'm going to do a bit of an overview of chlorination, although it's pretty thorough in itself. So we may, probably sort of refresh and go over more on chlorination next week as well. So here we go, or overview of chlorination. So we will look at its properties, the forms of chlorine used that they are classified as NSF 60 for drinking water additives. And for those of you who've never heard of NSF, it's the National Sanitation Foundation, and they set basically criteria or standards, that's what they are, for all kinds of chemicals, chlorine being one. We'll talk about chlorine's action, its reaction with water and other impurities in water. We'll talk a little bit about chloramination, breakpoint chlorination, and chlorine residuals. Okay, the properties of chlorine. Chlorine is a greenish-yellow gas with a penetrating and distinctive odor. It's 2.5 times heavier than air, which adds to some of its safety issues. We'll talk about that in our safety lesson as well. It has a high coefficient of expansion, meaning that its volume increases as temperature increases. So cylinders are typically filled to only 85% of capacity. It is non-flammable and non-explosive. As temperature rises, so does vapor pressure. So how will this affect the pressure in a chlorine cylinder as temperature rises? Why is this important? That's your little question, point of reflection. The forms of chlorine used. There are 4 types: gas, in which the chlorine is 100% available; solid, which is often called HTH, high test hypochlorite, or calcium hypochlorite. It's 60 to 70% available chlorine. Liquid, also known as sodium hypochlorite or bleach, and it's available 5 to 15%. And then there's the possibility of on-site generation. It is using a salt brine solution that makes sodium hypochlorite, in which only 0.5 to 8% of chlorine is available in that preparation. Okay. All right, the action-reaction of chlorine. The mechanism is not fully known, and it's sort of 2 questions about it. Does chlorine have a direct action against bacteria cells, or does chlorine's toxicity inactivate enzymes that allow microorganisms to use the food supply, to use up the food supply? Reaction with water containing inorganic and organic materials that form chlorine compounds. And the reaction in water continues until the reaction stops or it satisfies the chlorine demand. So we're going to get onto this in a minute when we talk about chlorine's reaction with water. So let me see. So when chlorine is added to water, a variety of chemical processes take place. The chlorine reacts with compounds in the water and with the water itself. Some of the results of these reactions, known as the chlorine residual, are able to kill microorganisms in the water. So, when chlorine enters water, it reacts with the compounds found in the water, and it will react with the organic compounds to form trihalomethanes. Okay. It will also react with reducing agents such as hydrogen sulfide, ferrous ions, manganese ions, and nitrite ions. Okay. So, the chlorine may be added in the form of gas, hypochlorite, or chlorine dioxide. All types of chlorine will kill bacteria and some viruses, but only chlorine dioxide will kill Cryptosporidium, Giardia, protozoans, and some viruses. Okay. So, this is what happens when chlorine gas reacts with water. It forms a hypochlorous acid and hypochloric acid. And here's the key point: the hypochlorous acid is the most effective form of free chlorine residual. You probably won't hear it called that all the time. You'll hear chlorine residual more frequently, but it is actually the hypochlorous acid that's formed with the chlorine and water reaction. So this reaction also depends on the pH of the water. The lower the pH is more efficient. It produces high amounts of the chlorine residual, or the hypochlorous acid. With high pH, it's less efficient, and you'll have higher amounts of the hydrochloric acid. Okay, let me see if I have anything else to add to that. So disinfection is more efficient at a low pH with large quantities of hypochlorous acid in the water, as I just said, than at a high pH where there is large quantities of hypochlorite atoms in the water, ions in the water. Okay. Next, we are going to look at breakpoint chlorination, but I think what I'm going to do is stop recording, and I'll see you in part 2. Thanks. See you soon. Talk to you soon.